All right, this is chemistry lesson 4.03, the Bohr model, where we finished talking about that hydrogen emission spectrum. So we said that if you look at the hydrogen emission spectrum, got a purple line, light purple, you've got a darker purple, you've got blue, and then you've got red. And there would be a little bit of a gap between the red and the blue, so the red should actually be about over here. But I didn't take down my paper yet. If you look at this diagram from this direction, this represents here in the center my nucleus, or the ground. In a sense, this first circle is going to be your ground state. So this is the ground state, this circle. Because the nucleus, the electrons don't go all the way back to the nucleus. So this represents the ground state. And if you look at these levels, this is like our atomic ladder in the last video. Now I'm going to go ahead and flip the page the other direction. Tape it down so it doesn't move on me. So in the last video, we said that Bohr figured out that the electrons, let's kind of recap, and I'm just going to go in black here, that the electrons existed outside the nucleus at fixed distances. So how do I sum that up? The electrons are located outside the nucleus in fixed distances called orbits. That's what he called them. That's Bohr's word. The second thing that he said was that the electrons could move away from ground from the ground state with the input of energy. So, for example, if my electron started here, it could go up 1, 2, 3, 4 rungs, or here it could go up 1 rung. The electrons didn't want to stay there, and so they would fall. And when they fall, when the electrons fell back or down, however you want to characterize it, they would release electromagnetic energy. So electromagnetic energy that was proportional to the distance they fell. So when the electron fell from here to here, this is a fixed distance. It would always release a wavelength of 656 nanometers. When it falls from here to here, it's falling down, boom, 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 boom. This would be like falling from the top of the ladder. It's releasing 410 nanometers. You might be saying, but wait a minute, this number is bigger than that number. Isn't this higher energy than that number? Remember, for wavelength, so is indirectly proportional to energy. The longer the wavelength, So there's a bigger distance between this wave and this wave, indicates lower energy. Longer wavelength, lower energy. So this has less energy than this. Well, that makes sense. This is falling back 4. This is falling back 1. What we see here is, this is the blue. And actually, I was a little bit off on this. This should have been the darker purple. And this should have been the lighter purple. So I grabbed the wrong purple here. But each one of these falls corresponds to one of these lines. The electrons couldn't go. Now, if an electron could fall from here to here, it's going to produce, let's see, if it could fall from here to here, it's going to produce green. If it could fall from here to here, it's going to produce yellow. But it can't do that. It can only fall back to these fixed places. And this was huge because what it did was it showed scientists kind of the general structure of electrons and that these guys were actually pretty advanced. Well, what do we have up here and down here? You've got more lines. Hey, Mrs. B, where are these guys? This is the Lyman series, and this is the Paschen series. Passion, I'm not quite sure how you pronounce it. But these wavelengths range from 1875 nanometers to 1994. And these range from 94 nanometers to 122. So tell me, which of these two has more energy? Did you say these guys? I hope so. Shorter wavelength, higher energy. These exist in the ultraviolet region. So these are UV. So that's one of the reasons why we don't stand and stare at the spectrum tubes forever, because they actually produce UV light too. This is going to be infrared. So if I had an infrared camera, or I could do an infrared spectrometer, I would see that there's other wavelengths that are produced. So we get 1, 2, 3 more wavelengths here, and this has got 1, 2, 3, 4, 5. But we can't see these with the naked eye. So these are the only 4. This Balmer series are the only 4 that show up in the visible spectrum. So this is actually the Balmer series. Now, you don't need to know that for the test, but I didn't want to leave you guys with an awareness of why we have more lines there. So to sum up, Bohr solved the mystery of where are the electrons and why do we get weird patterns for all the elements. So sodium is going to have its own unique set of, he realized, of orbits that are going to have its own transitions that was going to show up as a unique series, as a unique electromagnetic spectrum. So he realized that was true for all of the elements. And this unlocked now the study of electrons and how they transitioned. Because remember, we can't change protons if we want the same element. If I have lithium and I take away a proton, that gives me helium. But electrons change, and they don't just change a little bit. In fact, this was around 1910. The truth was actually much weirder than what Bohr could have imagined. Because he was right about the fact that we have kind of these fixed distances and that they could rise and fall. But he was wrong about orbits. And it took a couple of other scientists to help him, or to help figure that out and sort it out. And that's what we'll talk about in the next lesson. All right, that's it for now. Thanks for watching. Have a good day.